In the last class, we looked at the combined velocity triangles for Prandtl-Meyer expansion. So, this velocity triangle that we have here corresponds to this is the combined velocity triangle for a compressive wave solution, because as you can see, the flow after passing through the wave is deflected towards the wave. This is the compressive solution, and we looked at this solution also, which is the expansive solution. So, here the velocity vector after passing through the wave is deflected away from the wave. So, this is an expansion solution, and based on these two triangles we derived some relationship. Let us just recap these things quickly. We wrote u2 to be u1 plus or minus du, and we also wrote un2 as un1 plus or minus dun. And if you remember, un1 in both cases is equal to a1, which is the speed of sound of the flow approaching the wave. And based on the triangles, for example, based on triangle OPQ, so from triangle OPQ, we wrote PQ equal to u1 sine d nu, and for small values of d nu, this can actually be written as u1 times d nu. And from triangle PQR, we can write PQ is equal to dun cosine mu plus minus du, mu1 plus minus d nu, and for small values of d nu, this can be written as dun cosine mu1. And if we equate these two expressions for PQ, we get d nu is equal to dun over un times cosine mu1. Now, furthermore, from our velocity triangles, from triangle PQR, QR can be written as QR is equal to du, and that is equal to dun sine mu1 plus minus d nu, and for small values of d nu, this can be written as dun sine mu1. So, I can replace the dun here in terms of du, and if I do that, I get d nu is equal to du over u1 times cotangent of mu1. And if you recall the definition of mu1 is the Mach angle, and by definition sin mu1 is equal to 1 over m1. So, if you use that expression, that sin mu1 is equal to 1 over m1, then I can write this as du over u1 times square root of m1 square minus 1. So, here we have used the fact that mu1 is equal to arc sine 1 over m1. So, what we would like to do with this expression is same as what we tried to do earlier for Rayleigh flow, Fanov flow, normal shock and so on. We would even quasi one dimensional flow. So, the d nu is the change in the Prandtl-Meyer angle. We want to relate this to m1 alone. Okay. If you remember, for the oblique shock, we said that the theta, beta and m are related. Now, we know that the normal velocity approaching this is a1. Number one, and number two, the flow turning is also infinitesimal. It's an isentropic process. So, we want to relate the Prandtl-Meyer change in Prandtl-Meyer angle to Mach number alone. which means that I want to rewrite du over u1 in terms of m1 alone. So then I will have a relationship which I can integrate and get the closed form relationship. Okay. So we wish to express du over u1 in terms of m1 alone. So we do this by starting with the definition of the stagnation temperature T0 is equal to T1 plus U1 square over 2Cp. Or if I expand for Cp, I can write this as gamma minus 1 over 2 times U1 square over gamma R. Now if I take the differential on both sides, I can get dt naught is equal to dt1 plus gamma minus 1 over gamma R times u1 du. Now if I multiply and divide by a u1 and I multiply and divide by a t1 in this expression, I get dt1 plus gamma minus 1. Let me write it like this, gamma minus 1. So I am going to multiply and divide by a t1, so I have done that, and I am going to multiply and divide by a u1, so this becomes u1 square and this becomes du over u1. Right. So this ratio here, you can easily recognize this as Mach number square, right. This is equal to m1 square, so I can write this as dt1 plus gamma minus 1 times m1 square times du over u1. So dt naught is equal to this, and this is an isentropic flow, there is no heat addition or heat removal, which means dt naught is 0. So this is equal to 0. I am sorry, I left out a T1 here, so please make a note of that. So there is a T1 here in the numerator. So I can rewrite this expression then as d instead of writing dt1. Okay, fine. If you will allow me, I will drop the subscript on the dt1 and write it as dt over t1 is equal to minus gamma minus 1 times m1 square times du over u1. So I have just dropped the subscript 1 on the dt1 term, which is okay. That's all right. So what we have ended up doing is we have tried to relate du over u1 to Mach number, but in addition to that we also have a dt over t1. So we need to eliminate this now, because we want a relationship for du over u1 in terms of Mach number alone. So what we will try to do next is we will try to use the definition of Mach number to relate this to Mach number alone. So the definition of Mach number is m1 is equal to u1 over square root of gamma r t1. If you take the logarithm of both sides and differentiate, and differentiating, we get dm1, or let me write it as dm itself, dm over m1 is equal to du over u1 minus 1/2 dt over t1. This is very easy to show, it is not a problem. So now I have two relationships, one relating du over u and dt over t to dm over m, and another one also like this. So I can eliminate dt over t from this and I have the relationship that I am looking for. So eliminate dt over t, to get, I can finally write the following. it is convenient to write it like this: du over u1 is equal to square, I am sorry, pardon, a little bit ahead of myself. So, du over u is equal to d of m square divided by 2 times m square times 1 plus gamma minus 1 over 2 times m1 square. So, now I can take this relationship. So, finally, this is in the form in which I want it, du over u as a function of m1 alone, right. So, it is in the form in which I want it. So, I can take that and substitute that into this relationship here. D nu is equal to du over u times this. So, I can substitute for du over u from there into this, and I will be able to proceed and integrate. Let us do that next. So, we substitute for du over u1 into this expression for d nu. I get d nu equal to so d nu is equal to square root of m1 square minus 1 dm square divided by 2 m1 square times this quantity within parenthesis. Okay. Notice that so there is no flow turning if the flow approaches with a Mach number which is equal to the speed of sound, right. The Mach angle in this case is 90 degrees and that is an acoustic wave, so there is no flow turning in this case. Okay. It is an infinitesimally weak acoustic wave. So, nu is monotonically increasing function of m. M or m1 does not matter, m1 is the initial Mach number. So, I can actually integrate this, I can integrate both sides, right, from say nu equal to 0 to some value of nu, and the left hand side from m1 equal to 1 to some m. So, if I do that, what do I get? I get the following messy looking expression. M square minus 1. So, the angle nu is called the Prandtl Meyer angle. So, this is surprisingly we can actually solve this in closed form and we get this expression. The angle nu is called the Prandtl Meyer angle. So, notice that since nu is a monotonically increasing function of m1, we have to make sure that we calculate the angles properly for a compressive and an expansive solution. So, if the flow goes through an expansion, then nu actually increases, and if the flow goes through a compression, nu actually decreases. So, for a compression process, we have to write the flow turning angle theta is equal to nu1 minus nu2, because nu2 decreases. It is a compression process, m2 decreases, so nu1 minus nu2. So let me write it like this, nu2 less than nu1 because m2 is less than m1. For an expansion process, the flow turning angle theta is equal to nu2 minus nu1 because nu2 is greater than nu1 because m2 is greater than m1. Okay? So you have to be careful about this. Any questions? So we will do a couple of worked examples to illustrate the concepts and the ideas. All right. Yes.
Suppose flow of a flat plate is a supersonic flow. When that flow leaves that plate, what will be this angle, Prandtl mirror angle, at that particular point?
It is see the flow turning itself is not defined there. So the flow is going to be much more complex than what we have been doing so far. If it is leaving the flat plate, depending upon the ambient conditions, then we have to see how the edge is. If the edge is rounded, then it is going to go through an expansion process on both sides. So it will depend upon a lot of those things, how the edges are. Okay, so we cannot really say what it will look like for an arbitrary situation. It depends on how the trailing edge is, and depending on that we can say. If the trailing edge is rounded, for example.
Thin flat plate then.
Thin flat plate, then I would have to say that it's not going to have any effect. Then you have to use something called linearized airfoil theory. The flow will essentially feel only a very small disturbance. You may get an infinitesimally weak disturbance at the trailing edge and maybe at the leading edge. The first worked example reads like this: supersonic flow at m equal to 3, p equal to 100 kPa and T equal to 300 Kelvin is deflected through 20 degrees at a compression corner. Determine the flow properties downstream of the corner, assuming the process to be isentropic. We did the same example in the previous chapter, but assuming the compression process to be via oblique shock. So we have a compression corner like this. This is 20 degrees. So M1 is equal to 3. P1 static pressure is given to be 100 kPa and static temperature is 300 K. So this encounters a compression corner like this, and as we discussed in our previous class, we have a series of expansion fans, right? An set of expansion fan is generated from here, and this then coalesces into a normal shock. Right, as you make it smaller and smaller, the expansion fans coalesce. So we are going to look at then the flow is deflected like this. So we are going to look at what happens to the flow as it goes through the expansion fan.
Expansion fan or compression fan?
I'm sorry, yeah, isentropic compression process. It's a compression process, but you are going to have a, as we said, as the corner becomes sharper and sharper, the fan coalesces and becomes smaller and smaller. So eventually the whole thing will become an oblique shock, but what we are trying to do is to see how the compression process would be had it been isentropic. Let's say it's a small radius of curvature. Instead of being a sharp corner, there is a small radius of curvature. Okay, what is the process going to be like? So we use the tables for this purpose. For M1 equal to 3, the Prandtl-Meyer angles are tabulated in the in tabular form. So from the table we get for M1 equal to 3 we get nu1 to be 49.757 degrees. Theta is given to be 20 since this is a compression corner. Theta is equal to nu1 minus nu2, which means that nu2 is equal to nu1 minus theta, and if you substitute the values we get nu2 to be 29.757 degrees. So from the tables, for this value of nu2, we get M2 to be 2.125. And the static temperature T2 is equal to T2 over T0 times T0 over T1 times T1, and I can get T2 over T0 from isentropic table and T0 over T1 also from isentropic table, right? I know the Mach number. So if you substitute the values you get this to be like this, 0.5254575 from our isentropic table times T0 over T1, I am sorry, not times, so I am going to do this, divided by 0.35714 times 300. So this comes out to be 441 Kelvin. And we also calculate the static pressure downstream in the same way, P2 equal to P2 over P0 times P0 over P1 times P1. And if you substitute the numbers from the tables, you get this to be 386 kilopascal. Of course, there is no loss of stagnation pressure. It is an isentropic compression process, so P02 is equal to P01. So the same shock, had it been through an oblique shock, we worked out this example in the previous chapter. So had this been an oblique shock, the corresponding numbers would will look like this. The Mach number for that case comes out to be 2.0, and the static temperature for that case comes out to be, or came out to be, let me see, did we calculate that? Yes, 470 Kelvin. So 470 Kelvin. Let me write it down here. 470 Kelvin, and the static pressure came out to be 377 kilopascal. And P02, here P02 is equal to P01. In the previous case there was a loss of stagnation pressure to the amount of 20%. So P02, write like this, times P01. Okay, so now the stagnation pressure is the same. For a fully oblique shock, there is a 20% loss of stagnation pressure. So this is 0.8. I am sorry, 0.8 times P01. So again, you see that both the these values are considerably different from what we had seen earlier for the oblique shock. Yes.
So in isentropic compression, P2 is 386, and in oblique shock compression it is 377. But in oblique shock it should be more than the isentropic compression.
This is an oblique shock, so you have to look at the effective Mach number and then see whether it is going to be greater. See, you are comparing normal shock with isentropic compression. Here the normal shock component is happening only for Mn1 and Mn2. So, you have to be a little bit careful about interpreting these numbers that way.
But both the floor is having same angle, na? Means deflection angle is the same, na? For isentropic also and for oblique shock also. In oblique shock, then P2 should be higher than isentropic.
But you are looking at the compression taking place in different frames of reference. The normal shock compression for the oblique shock is only for the Mn1, and that is not although M1 is equal to 3, this one is less. Yeah, so
static, we are considering static, it is independent of
that is correct. No, that is correct. But what I am saying is this is fully isentropic. This is not a normal shock. The curves that we drew earlier were for normal shock. So for an oblique shock, whether it will hold or not is something that that is not really straightforward. So it can happen this way. For normal shock, yes, the normal shock always gives you higher values of pressure and temperature compared to isentropic compression for the same change in specific volume. Remember, there are many constraints there. For the same change in specific volume, this is true. Here we are not comparing for the same change in specific volume. I have not said what the change in specific volume is. So, you cannot directly say that it should be like that. Okay? When you are comparing two curves, what are the limits against which you are comparing is also important.
And then there will be a slip line where
No, definitely there will be a slip line across this, yeah, because the entropy here will be higher. So, there will be a slip line as we drew in the previous class. So, there will be a slip line like that, yeah.
But about slip line, pressure should be same, but now pressure above slip line, below slip line is different.
No, the thing is, as you bring this closer and closer, you are going to have a complex interaction here in this region. The slip line itself may not be just a slip line. So, to equalize the pressure here, you can have, for example, an expansion phase which originates from the corner here and then goes out. Slip line need not be just a discontinuity. Slip line can also create additional flow structures to equilibrate the pressure. Our theory is really very simple. We are doing hand calculations. So many of these complexities we cannot assume or we have to idealize. Okay, so that is one worked example. The next worked example that we are going to do is, here we looked at a compression corner for 20 degrees. Let us see what happens if this is an expansion corner of 20 degrees. So, this is 20 degrees now. So, we have flow at the same Mach number M1 equal to 3, which approaches the expansion corner like this, and we are going to generate. So, this corner generates an expansion fan. The initial angle is, let us say this is the first expansion, first Mach wave like this. So, this has a direction like this. The last one will presumably go something like this, and the flow is deflected around this. So, the flow goes through and then it becomes parallel to the wall. So, this angle is mu1, and this angle with respect to the, remember this angle is always measured with respect to the velocity vector that is approaching this, right. So, that means this angle is going to be measured against this velocity vector. So, this is mu2 . So, from the tables for M1 equal to 3, we have mu1 equal to 19.471 degrees, and mu1 we had already calculated 49.757 degrees. Now, this is an expansion corner. So, nu increases across the wave. So, that means theta is equal to nu 2 minus nu 1. So, which implies that nu 2 is equal to theta plus nu 1, and if I substitute the values, I get this to be 69.757 degrees. So, you can see that nu increases across the expansion fan because it is an expansion process. So, for this value of nu 2, we can get from the table m2 to be 4.32 and mu 2 to be 13.384 degrees. Notice that mu 1 is measured with respect to u1, mu 2 is measured with respect to u2, which is now parallel to this wall, right. So, in between these two you have an expansion fan which looks like this. Okay. Now, having something like this is a little bit inconvenient for the kind of analysis that we are doing. So, there is an approximation that we can make. The approximation is for this value of m1 and this value of turning angle and this value of m2, can we replace this expansion fan with a single wave? Remember, single expansion fan for a finite turning angle is prohibited by second law. But for approximation purpose, for calculating reflection and so on, see, if you want to calculate the reflection of such a fan, then you have to look at reflection of each one of these waves. It becomes very cumbersome. So, effectively we can actually approximate this fan with a single wave. It is an approximation, not realistic, for purposes of hand calculation further down. That is something that is customarily done. So, let us just see how that is done just for future use. So, single wave approximation. Remember, this is an approximation. So, the emphasis is on the word approximation. Such an approximation will allow us to actually calculate, do the hand calculations a little bit more. We can actually look at expansion and reflection of an expansion fan and so on. Okay. So, this is made under same conditions. M1 theta and M2 remain the same as before. So, we do not change any of this. So, what we do is we calculate an average angle for this single wave. Let us call that mu bar. This mu bar can be calculated in several different ways. For example, the simplest thing is to take mu bar to be the average of mu 1 and mu 2, or a slightly better approximation is to calculate the mu bar like this. Take it as the average of the Mach number rather than average of the angle. And this mu bar is measured with respect to, so this angle measured with respect to theta bar, which is theta 1 plus which is theta over 2. So, which means that what I am doing is the following. Let me draw a separate diagram. So, these were the initial and final Mach waves. and let me see, unfortunately it has come out like this. Let us say that this is my, this angle let us say is theta over 2. So the single wave that replaces all this looks like this. And this angle is mu bar. So that angle is measured with respect to theta over 2. So that is mu bar. So we replace this entire fan with a single wave like this. This is an approximation. Such a solution is not allowed, but it is an approximation. It is a very good approximation for the kind of hand calculations that we are doing. We can actually deal with reflection of a single wave much more easily than reflection of an expansion fan, which contains an infinite number of waves almost. It's a very useful approximation for engineering calculations. The usefulness of this approximation will become apparent when we do the next worked example. The next worked example is a continuation of our earlier worked example. If you remember, we looked at this example before and we had actually calculated flow properties up to section 4. Now we are going to actually go ahead and look at flow properties in section 5. Okay? Let us see what happens with this. So before we do that, we need to look at one concept, which is reflection of an oblique shock from a constant pressure boundary. In the previous chapter, we looked at reflection of an oblique shock from a wall or a solid boundary, and we saw that an oblique shock is reflected back as an oblique shock from a solid boundary. That was what we looked at in the previous chapter. Now we are looking at a situation where, let's say we have a jet boundary like this and an oblique shock somehow is triggered, and so this is a, say, jet boundary or a constant pressure boundary. So pressure is the same across the across this. So pressure is P ambient here along the jet boundary, and an oblique shock wave is incident let's say like this. So that was the situation that we were looking at. If you remember, our previous solution looked like this. We had so this was what we were looking at, and then we wanted to see what happened after this. So remember this region, this was at P ambient, this was at P ambient, and now this is going to be reflected. So this was at P ambient, this was also at P ambient, and now the jet is impingement, the oblique shock is impinging upon the jet boundary, and we want to see how it comes back. So if I focus my attention on the point of impingement here, okay, so when the when the oblique shock impinges upon the jet boundary, the pressure increases, right? Pressure always increases, static pressure always increases across the oblique shock wave. However, the point of impingement now is on a boundary which is exposed to the ambient pressure, which means the pressure there always has to be the same as the ambient pressure. So, the impingement of the oblique shock causes the pressure to increase. So, the increase in pressure must immediately be relieved by an expansion fan. So, an oblique shock, when it impinges upon a constant pressure boundary, this is reflected as an expansion fan. So that at this point the pressure is always ambient pressure. We saw in the earlier chapter that oblique shock impinging on a wall is reflected back as an oblique shock, and the angle depends upon the angle of the wall or the point of impingement. In this case here, because it is a constant pressure boundary, pressure has to remain constant. The increase in pressure due to the oblique shock must be immediately offset or relieved by an expansion fan, which brings it back to which brings this point back to the same ambient pressure. Okay. So, that means what is going to happen to the pressure in this region? Pressure in this region is higher, correct? That is what we are looking at, and the pressure in this region will continue to be ambient, because we are going to have a set of expansion fan coming from here also. Right. This is what is shown in this figure. So, you can see in this figure that the oblique shock impinges at this point, and there is a generation of an expansion fan from that point which goes down like this. Similarly, the point of impingement of the oblique shock from above is here, and once again we trigger expansion fan from here. So, the pressure in region 5, remember region 5 is now in direct contact with the atmosphere, separated only by a jet boundary. So, that means pressure in region 5 is P ambient, same as outside. Okay. So, when an oblique shock impinges on a wall, it is reflected back as an oblique shock. When it impinges upon a constant pressure boundary, it is reflected back as a wave of the opposite kind. Notice that when this expansion fan impinges upon the jet boundary here, for the same reason that we mentioned, it will be reflected back as an oblique shock wave, right? Because the pressure at the point of impingement tends to be less than atmospheric pressure, so we must trigger an oblique shock like this. But the reflection of a fan from a jet boundary is much more complicated, so the flow situation becomes more complex for the downstream, which is the reason why we discussed replacing a fan with approximating a fan with a single wave. So, then the reflection calculations become easy. We can actually proceed a little bit more with hand calculations, but now if it is a fan, we cannot do that. Okay, that is the usefulness of the single wave approximation for the expansion fan. Although it is not seen in reality, it makes our life easy because we can do hand calculations a little bit more. Okay. So, what we are going to do now is do the calculation, continue the worked example. So, let me summarize our findings here. An oblique shock is reflected as an expansion fan from a constant pressure boundary. And vice versa.
So,
yeah.
This will change flow direction also then.
Which one?
Expansion fan. Flow won't be parallel to axis then.
No, flow will not be parallel to the axis. The flow is now going to be deflected away from the wave. If you remember, in the previous case, the flow vector was actually like this. It was about 3 degrees above the horizontal on the top side. Now, because it is going to be reflected away, it may be brought back to the horizontal, but there is no guarantee that it will be like that. So, in the previous case, it was not horizontal, it was like this. Now, we have an expansion fan, so the flow is, the flow is going to be turned further away from this, it's going to be turned further away, which means that the jet has to swell now, because there is also an expansion process, so the jet is going to swell, and that is what you are seeing here. So, you can see that the jet now begins to swell on both sides, right, and the flow is actually deflected away. Equilibration of the velocity vector will take much longer. What is more important is equilibration of the pressure. So, from our previous example, we are going to continue that now, and if I remember, let me just write down a few things just to refresh our memory. We had P4, static pressure in region 4 was 220.24 kilopascal, static temperature in region 4 was 208 Kelvin, and Mach number, can someone tell me what the Mach number was? M4. .48. Okay. So, based on our discussion so far, P5 is equal to 100 kilopascal. P5 is the ambient, is equal to the ambient pressure. So, P5 is equal to 100 kilopascal. And the previous calculation also gave us P04 to be equal to 785 kilopascal, right? So, the previous calculation gave us P04 to be 785 kilopascal. The expansion fan is an isentropic process. So, in this case P05 is also equal to 785 kPa, since the expansion is isentropic. So, P5 over P05 is equal to 0.127065. So, this implies that M5 is approximately equal to 2. So, the Mach number increases to 2. So, T05 is 300 Kelvin. So, from the tables I can get T5 over T05 is equal to 0.5556. So, this implies that T5 is equal to 167 Kelvin, since T05 is equal to 300 Kelvin. That was given at the beginning of the problem. Now, we are also asked to calculate the angle that the edge of the jet makes with the horizontal. Let us calculate this and finish the problem. So, from the tables, for M4 is equal to 1.48, we get nu 4 is equal to 11.3168 degrees, and for M5 equal to 2, we get nu 5 is equal to 26.3795 degrees. This is an expansion process. So, the flow deflection angle in this case is going to be nu 5 minus nu 4. So, that is equal to 15.0627 degrees. Now, this 15.0627, remember, is the flow deflection angle with respect to the previous velocity vector. So, that means angle made by the jet boundary with the horizontal is equal to 15.0627 degrees. That is turning in, this 15.0627 is turning away from the wave in this direction, and the previous oblique shock turned it through an angle of 14.6834 degrees minus 11.2118 degrees. So, these are numbers that we have taken from our previous example. Remember, this is turning in the counterclockwise direction, this is also turning in the counterclockwise direction, this is turning in the clockwise direction. So, let me put it like this. So, this is turning in the counterclockwise direction, this is also turning in the counterclockwise direction, this is turning in the clockwise direction. So, if I calculate the algebraic sum, I get this to be 18.5343 counterclockwise. That is the angle that the edge of the jet makes with the horizontal. So, this example concludes our discussion of gas dynamics. We have completed all the chapters in gas dynamics. What we will do from the next class onwards is start our discussion on propulsion. Okay.